Solving rational inequalities. Example: solve the inequality x minus 4 over 2x plus 4 is greater than or equal to 1 algebraically. Step 1. Subtract 1 from both sides of the inequality. We want 0 on one side. Now we want to simplify, so it's necessary to get a common denominator in order to subtract fractions. Note, 2x plus 4 over 2x plus 4 is equal to 1 for all values that it is defined for. Now subtract only the numerators. We have x minus 4 minus 2x plus 4 all over 2x plus 4 is greater than or equal to 0. When we distribute the minus and combine like terms, we obtain negative x minus 8 all over 2x plus 4 is greater than or equal to 0. Step 2. Determine the real zeros of the numerator and the denominator. Set the numerator equal to 0. We have the equation negative x minus 8 equals 0. Solving for x, we find that x is equal to negative 8, the real zero of the numerator. Setting the denominator equal to 0, we have the equation 2x plus 4 equals 0. Solving for x, we find that x is equal to minus 2, the real zero of the denominator. Step 3. Plot these zeros on the number line to divide it into intervals. Note 2 zeros will divide the real number line into 3 subintervals. We would like to define them. The first one is from minus infinity to minus 8. Then we have a subinterval from negative 8 to negative 2, and another from minus 2 to positive infinity. We will use a table to analyze these intervals. We would like to choose a number within each subinterval. Any number is acceptable. For the first interval, negative 10 is a nice integer in between minus infinity and minus 8. The largest integer in the middle interval is negative 3. We want to choose simple values, easy to evaluate, so 0 is a good choice for the third interval. So we're going to place those into our simplified rational expression minus x minus 8 all over 2x plus 4. When we allow x to take on the value of negative 10, in that expression we get negative 1/8. Evaluating at negative 3, we obtain 5/2. And evaluating at x equal to 0 as a test point, we find the value of negative 2. What we are interested in is the sign of the interval, and so whatever the sign turns out at the test point, that is the sign of the rational expression on the entire interval. It's negative on the leftmost interval, but in the middle interval, the rational expression is positive. So that's part of our solution, and it becomes red. The third one, the rightmost interval, is negative. We want to include the value negative 8 in our solution because it's where the rational expression is equal to 0, so we change the round paren there to a square paren. We should not include the endpoint negative 2. The rational expression is undefined there, so we leave that as a round paren. on negative 2. The solution to our original problem, x minus 4 all over 2x plus 4 greater than or equal to 1, is the interval from minus 8 to minus 2 closed at minus 8 only, or the set of x such that negative 8 is less than or equal to x, which is less than negative 2, since on this interval the rational expression minus x minus 8 all over 2x plus 4 is greater than or equal to 0. Example, solve the inequality x squared minus 2x plus 1 all over x squared minus 4 is less than 0 algebraically. Step 1, factor the numerator and denominator completely. Note 0 is already on one side. Step 2, determine the real zeros of the numerator and the denominator. Setting the numerator equal to 0, we have x minus 1 all squared equal to 0. Take the square root of both sides of that equation. We find that x minus 1 is equal to 0. Adding 1 to both sides, we solve for x and find x is equal to 1, the real zero of the numerator. Setting the denominator equal to 0 and solving, applying the zero factor property, setting each factor equal to 0 and solving individually, we find that x is equal to 2 and x is equal to negative 2, the real zeros of the denominator. Step 3. Plot these zeros on the number line and divide it into intervals. We see that 3 zeros will divide the real number line into 4 intervals. We want to identify these. The leftmost is from minus infinity to minus 2. Next, we have an interval from minus 2 to 1. The next subinterval is from 1 to 2. And the last one is from 2 to positive infinity. We will use a table again to analyze these subintervals to determine where the rational expression is less than 0. That is what our solution is. So we will choose a test point or a number in each of these intervals. The largest integer in the leftmost interval is negative 3. That's why I'm picking that number. It's 0 is in the next interval. You can pick any number in that interval. I like 0 because it's easy to evaluate the expression. The third subinterval from left to right has no integer value, so I'm going to pick a simple rational value of 3/2 right in the middle. And the smallest integer in the last interval is 3. That's why I'm picking that. No other reason. Just trying to simplify my work. Now we are going to evaluate the expression at these test points. When we substitute negative 3 for x in our expression, we get 16/5. The value of the rational expression at 0 is negative 1/4. Evaluating at 3/2, we have negative 1/7. And allowing x to equal 3, we get 4/5. Again, the only thing of interest here is the sign of the rational expression on each interval. It is positive on the leftmost interval, not part of our solution. From negative 2 to 1, however, it's negative. That's part of our solution. It's becoming red above. From 1 to 2, it is also negative, so that is part of our solution. We're going to include that in our answer. On the last subinterval, it's positive, not part of the solution to this problem. It's important to note that none of the endpoints are included in our solution. It is undefined at negative 2 and positive 2, and it's equal to 0 at 1. We have strict inequality in this example. Our original problem, x squared minus 2x plus 1 all over x squared minus 4 less than 0, is the interval from negative 2 to 1 union the interval from 1 to 2, all open intervals, or the set of x such that negative 2 is less than x is less than 1, or 1 is less than x is less than 2. Since on these intervals the rational expression is less than 0.